It's that time, so I want to welcome everybody for another CAIS seminar. The first thing I would like to do is express a very warm welcome to our new CAIS coordinator, Ushija Dezoisa, sitting here. As you know, we've had a temporary coordinator, Colleen Plymouth, for a few months, and now we have settled to Ushija. Ushija has a great background. She's a Yorkie through and through. Obtained your Bachelor of Science degree here, and your Master's degree in Education, which is completed now, I think. And has extensive experience as a coordinator with two other boards, as well as research project management experience in physics here. So we're really, really excited to have you join the team. And so let's express a warm welcome. So I'm also very, very excited to host for the first time our colleagues from AMD. So most of you know that AMD has a very interesting location in Markham, very near our new campus. I think there's a lot of cool things happening there, so we're going to find out a bit about some of those things. So specifically, we're welcoming Dr. Mehdi Saidi, so from left to right, and then Alex Can, and then Calvin Louie. Calvin, not Kevin. He's told me that you can just call him Absolute Zero.
Yeah, sure.
So Calvin is a senior manager at AMD, and I think an enabler for collaborative research. We're going to hear specifically from Mehdi and Alex. So Mehdi is the AI lead and feature architect for machine learning-based non-playable characters in video games. Just got that off your website. And research interests are quite broad in reinforcement learning, robotics, graphics, and AI. I think that's what we're going to hear about now. But you have a background in quantum computing.
Yes, I do. Yeah.
Which maybe we won't hear about in the talk, but you can always ask him questions. And Alex, his colleague at AMD, is the lead developer of Schola, which I guess is the reinforcement learning environment you're going to talk about, and has research interests in deep learning, reinforcement learning, and AI in games generally. So, so very pleased to have you here. Really excited to hear about what's going on in AMD.
Thank you. It's a pleasure. So I'm going to start. Thanks, James, again for your nice introduction. And then it's going to be, it can be an interactive discussion, right? Please feel free to ask any question as we move from one slide to another. So the agenda that we have today is we are going to put some light into this new release SDK that we have. We call it AMD Schola. And we are going to see actually how to train agents, and we are going to define what agent means in Unreal Engine. And the reason that it's going to be interesting is basically the reinforcement learning part. But I'm going to motivate it first from video games perspective, and then I'm going to just take it slow, go over reinforcement learning, and then Alex is going to cover some software aspects of the Schola, and then I'm going to come back to sim to real and digital twin. Let's get started. I guess, so video games, some of you are playing video games, right? Video games is important not because actually you play. You play video games, somebody is going to watch that, right? So you are basically part of a family. They are going to be affected by how you play the games, right? So it's not just whoever is playing the game, it's the whole community that's going to be impacted by video games. So that's basically one dimension of it, right? The other dimension is whatever you cannot do in real life, usually you can do in video games, and that's basically something very interesting. Usually people say actually it's a kind of platform for fostering creativity, from content creation to whatever impact that you're going to have for society, right? Everything is going to be impacted by these video games. And so it's important to be part of it, a good part of it, right? AMD in particular, as you know, we build GPU, CPU, NPUs, right? And people use these things for different purposes. One of them is to play games, right? So it's important for us to understand actually where the industry is going, and to be able to be part of it, obviously ML is going to be very important here. So I'm going to talk about what ML can do in video games. Then I'm going to cover traditional AI in video games. Then we will discuss reinforcement learning and why it is interesting. Then we will cover AMD Schola with some examples, and then we deep dive into the concept of digital twin and real scenarios. I guess to get started, if you ask, let's say, ChatGPT, right, how ML can be used in video games, you are going to see a lot of different possibilities. You can just create non-player characters. Non-player characters or NPCs are the ones that you cannot control, right? So when you play video games, you play something, and then there are other things in the scene that are there to make the game fantastic, right? Those are non-player characters, and we call them NPC. For example, if you are fighting against a boss NPC, that boss NPC is basically the NPC, and you are fighting against it, right? Or if you just do a race car, the car that you are controlling is just your character. The other cars in the scene are non-player characters. So you can basically use AI to control this. You can generate content with AI, right? Procedurally generated. So you saw all these videos that people generate for advertisement with AI, right? The question is when we are going to see those to create content for games. We already see a lot of those, right? But as we see progress in AI, it's going to be more consistent in terms of the different time that you see at the video and everything. You can enhance graphics, you can test the game with AI, you can make the game harder or easier depend on your expertise in that particular game, right? So they call it personalized gaming experience. And you can talk to characters and basically have dialogue with them, right? So you can use AI for different perspectives. Now, looking at one specific NPC, right? So let's assume that you have Alice and Bob in the game, right? And Alice wants to go to Bob. Traditionally, we all pass these computer science courses that talk about shortest path, right? Dijkstra's algorithm and all those things, right? You can use graph theory to find the shortest path between Alice and Bob, right? And then if it's static, it's going to be easy. If it's dynamic, you need to change the graph whenever actually there is a change in the environment to update the location to update the road from Alice to Bob. That's basically one way of doing this, but it's going to have a lot of compute, right? And at the same time, it's kind of very predictable because Alice and Bob and shortest path is predictable, right? You can randomize it a little bit, but still, with AI, you can do much better. So that's basically called nav mesh or navigation mesh. And then in the other side, you have this finite state machine. When you know actually what's going on, game developers say you are in a patrol mode or chase mode or attack mode. And whenever you have an NPC in the game, right, you basically know which state you are. And based on this finite state machine, you are going to develop these characters. So if you are in patrol, so you are going to just move around. If you are in the chase mode, you're going to follow a character. So everything is predictable by game developer. They basically sit and design these things for a long time. And then when you play the game, it's going to be based on what they program. And then the last one is basically just a nav mesh, right? So in this one in particular, the green areas are the one that character can walk over, right? You see, for example, when the game developer developed this, they decided that it's not walkable here, and then it's walkable here. And then when you play the game, you cannot walk over something, right? You cannot jump from the window if the developer didn't decide to do it, right? And that's basically the way that traditional AI is used in game. Now, the thing that actually I want to highlight is the concept of reinforcement learning. Reinforcement learning is really very interesting because of the fact that you learn through interaction with the environment. Let's go back to a very simple example. So if you want to teach your dog to do something, right? So the dog is going to do something, you say good dog or bad dog, or good girl or bad girl, right? And then the dog is going to get this feedback, and then next time the dog is going to do it. And then you do it a lot, and then the dog is going to learn. So this interaction with environment and the feedback that it gets is the concept of reinforcement. So you are reinforcing something, and the dog or the agent in general is going to learn by reinforcement. Why this is important, right? So you learn how to bike, right? In that case, you cannot just watch actually somebody to bike and to ride a bike and then learn from it. There is no way that you can just learn by watching, right? If Professor James in a class teach you to just ride a bike, right? You are not going to ride a bike. The only way you can ride a bike is basically to try, to get feedback from environment. If you just do this, you're going to fall off, right? So this interaction with environment is the concept of reinforcement learning, and not everything can be learned through supervised learning and teaching and everything, right? So we need this reinforcement learning for sure in basically learning paradigm to be able to learn new things. And the concept actually is used in real scenario, in games and in many different things as well. So for example, we have this concept of teacher-student, which is supervised learning, or you learn on your own, or you basically interact and you learn first this, and then when you learn this, you're going to learn a real one, right? So this is the concept of reinforcement learning that I'm going to talk. In this domain of reinforcement learning, there is a concept of agent, the character that is going to learn, and then the agent is going to do some action, right? So for example, controlling the paddle or controlling the handle, right? These are the actions that the agent is going to do. The agent is going to observe something. So for example, if you observe there is an obstacle, so you are going to react to it, right? So that's observation. So you can observe with your eyes, your ears, right? If there is a noise, you see actually something is going to happen, and then you take some action for it. There is an environment that you interact. If, for example, the environment is just a flat road, then you're going to do something. If it's kind of bumpy road, you're going to do something else, right? That's your environment. And then at the end, you have a reward, right? Whenever you do something, you're going to get rewarded. Remember how basically toddlers learn to walk, right? So basically, they just extend their hand, right? And then they learn something because there is a reward. They see actually if they extend their hand, they can just reach along it, right? And that's basically the reward that they get from the environment. So if we understand reinforcement learning, there is an agent, there is an environment, the agent and environment are going to interact. The agent is going to get something out of this environment. We call it formally a state. That's basically the observation that we talked about. Formally speaking, it's called a state, and we are talking about a timestamp. So in timestamp t, the agent is going to observe a state st from the environment, and then the agent is going to keep a policy, which is basically the brain that the agent is going to have. And it's going to be interactive, right? It's going to be a closed loop. The agent is going to do an action, and then we see what's going on in the environment, another state, another action, another state, another action. And then we do this over and over until the agent learns some actions are good, some actions are bad. And this is the way that actually the agent learns. As we do this loop, right, we are going to have a lot of things, including this reward, right? So whenever the agent takes one action, there is going to be a consequences. The consequences can be good or bad, and that's basically the reward that the agent gets. And overall, as an agent in the environment, you want to maximize the total reward that you get, right? So you don't want to just get the best reward in the next step. You want to get the best reward overall. So if you want to learn to bike, if you just do something to not fall right now, it's not enough. You just need to keep your journey or your trajectory, right? Now I'm going to basically put everything in a picture. Let's assume that there is a grid world, right? And you want to take these possible actions up, down, left, and right to reach a goal. And whenever actually you take one step, you're going to get rewarded by -1, which basically means if you get to the goal fast, you're going to have better reward, right? So because it's -1. So you need to do it fast. And let's see actually how you're going to do it. This is a random policy. In each location, you can pick whatever you want, right? So there is no hope here, it's a random policy. And if you consider an optimal policy, you see actually when you are here, the optimal policy is to go up. When you are here, the optimal policy is going up. For example, when you are here, the optimal policy can be going up, going up, going left, or right, right? Because in all cases, there is 2 steps to the goal. So that's basically the definition of optimal policy. Now, the goal is basically to start from this random policy and to end with this optimal policy, right? And we want to do it with reinforcement learning. Let's do it in practice. So these black cells are basically the goals, and this cube here is basically our agent. The agent is going to try to start from a random location and get to a target location. And as you see, everything is randomized because we don't want to just teach the agent to go from here to here. We want to teach the agent to start from anywhere and get to the basically to one of possible destinations, right? So for example, if I consider you as an agent, if you are in a campus, right? So you know how to get to a cafeteria, and the cafeteria can be different cafeteria, depends on where you are, right? So this agent is responsible to get to one of these cafeteria, for example, and then depends on where it is, it's going to observe the whole map and then basically try to get it. Now, obviously, when you start training, everything is bad, right? During the train, as you see, we use a generic 9x9 grid. So in this case, because it's generic, the agent actually, everything is randomized, and then we fixed it during the test, and then ask the agent to start from somewhere random, and then see actually how it works. On the other hand, here, we basically train on one specific grid, right? We always train agent for this location. So for example, if you live in a city, you already know where things are, right? So you are trained with that specific grid. It's not going to change every day, right? And then you are getting smarter and smarter, and you already know what's going on. But if you move to a new city, then things are different, and you need to be able to use that there, right? And that's basically the concept of generalization. As you can see, so this is kind of very optimal, very close to the optimal policy. If you start from each location, there is basically an arrow that shows you where to go and how to get to the closest destination. However, if you apply this in a generic grid, you see actually sometimes it's optimal, and you need to be in the environment more and more, because that one is after 1 million steps, right? If you need to be in the environment more and more and interact with the environment, so you are going to get better and better. With that, I'm going to hand it over to my colleague Alex to talk about how we do these things in Schola, and then I'm going to continue with it. Thank you.
Thanks, Mehdi. So yeah, I'm going to talk about AMD Schola, which is our plugin for Unreal Engine, which I'll go into a little bit in the next slide, for training reinforcement learning, agents, and kind of generating simulations using Unreal Engine. So Unreal Engine is one of the most popular game engines, right? So this is basically a framework for building games and environments in games, right? So it has tools like visual scripting languages built into it. It has modeling. It has frameworks for handling like raycats, light, anything you would want, animations. It's also used for making movies and other kind of animations that way. Yeah, in general, this is probably the most popular framework, right? You've heard the game Fortnite, that's built on top of this, and this is released by the same company, Epic Games. So this is really kind of one of the most like key like platforms in the gaming industry, right? So that's kind of why we look at it as where we want to basically introduce RL and kind of bring that together here, right? So what does Schola do for training your models with RL? What we do is we basically link Unreal Engine to a bunch of these popular open source RL frameworks written in Python, right? So Gymnasium is an open standard for defining an RL environment. Stable Baselines 3 and RLlib are more targeted at training, right? So they provide algorithms, models, that sort of thing, so that you can train an RL agent quite quickly, right? And then so what we do is we basically take your scene that you've built in Unreal Engine and then basically create a Python environment representation so that you can then immediately plug it into Stable Baselines 3 or RLlib. Or if you have another framework, right, most of them support basically linking to Gymnasium, previously called Gym, and so then you can do it that way, right? So let's say you've gone through and you've trained your model with SB3 or RLlib, then you want to deploy it in an actual game or maybe in a different platform. So like, let's say you want to deploy it on a robot, right? What you do is we provide tools to basically remap those outputs to an Onyx model. Now, granted, the frameworks both support going straight to Onyx model as well, but we adapt it for use inside Unreal Engine. This is not necessarily necessary if you are looking to use it in a different place. Basically, you take your output, you turn it into an Onyx model, and then if you want to run it in the game, you can deploy it kind of inside Unreal Engine natively, so you don't have to kind of go back and forth between Unreal Engine, which is C++, and Python, which is where all the popular machine learning stuff is. So I'm going to give a bit more detailed overview or detailed breakdown of how you actually build things with Schola. So to start, I'm going to kind of go back to this picture from Mehdi, right? So in kind of our standard reinforcement learning system, we have an agent, right? The agent has a policy that maps a state to the next action, right? The action is then fed into the environment, which translates that action into a reward and a next state, right? It updates kind of what's happening. Right? And then we feed that reward and next state back into the agent to take the next step and also do any updates to refine the agent incrementally, right? So we kind of have these key ideas, and they're going to be on the left here, right? And we have 5 key kind of concepts in Schola that remapped across these key kind of hypothetical reinforcement learning building blocks. So the first one is kind of this idea of actions, right? So we provide essentially a set of pre-built actions, but also an interface that's implementable to, basically create your own action quickly, and then that gets translated into like the Python environment, and it shows up in Gym, RLlib, SV3, right? So a couple of quick examples of kind of very simple actuators to build. We got a rotation one here that just the little dude's rotation is controlled by the policy, right? One where it teleports, so this one, okay, in this example, it's teleporting on the Y dimension 200 per step, or a movement input one that kind of mirrors how a player would move the agent with a joystick or something like that, right? And then very similarly, we have observers for representing observations, right? So this is kind of how it sees the state of the game, because the whole game state is extremely complex, especially for an engine as detailed as Unreal Engine. Right, so here's a couple simple observers. We have a position observer that just tells the agent where it's located, right? In this case, it's an absolute position, but you can do relative. You can do an egocentric one where it's basically rotated and rescaled and repositioned around the agent. So it's kind of like, instead of saying that bin over there is at location 200, well, it's actually like 200 units to my right. We have this idea of a raycast sensor kind of mirroring a LiDAR, fire some rays, return whether you hit anything. Maybe return some kind of information about the thing you hit, right? Or another, another counterexample is the rotation sensor that just says what's the rotation of this agent. Pretty simple stuff. But Unreal Engine is like a very powerful tool. So once again, we also provide kind of like an open, simple API that just says bring your own kind of, put whatever you want here, and then it'll get remapped into Python, right? So. To represent kind of the policy and some parts of the environment, we have this idea of a trainer, right? So it has a few utility functions for resetting it, for handling things that happen when your training episode ends, right? So this is like, if you're learning to ride a bike, the episode ends when you fall off the bike, or maybe you reach some goal, right? So maybe you want to do some setup, you want to do some cleanup, you want to check a few things, right? So we have stuff for that, and just also some stuff for basically passing arbitrary information between Unreal and Python. Right, so the actual meat of the trainer is in these kind of 2 functions here, which is where you can check whether predict whether the environment is done or what the reward is, right? And if you haven't seen it before, this is what Unreal Engine calls blueprints. So it's a visual coding language that's designed to be essentially for game designers rather than game developers. So a game developer would write a system in C++ that would expose some stuff to blueprints, right? So in this case, the system exposes essentially a callback, right? Then this runs this function here, and the white nodes are execution, right? So you could read this as we enter the function, we call the return node, and then it goes backwards to figure out what the return value is. In this case, it's just 0.02. And similarly here, right? We started the compute status, we go to return node, go backwards to this value here that selects what the return value is. And this is basically just a blueprint if statement that says if the ball is touching the wall, return completed, otherwise return still running, right? And you could think of this as being the status for a Pong game, right? If the ball hits the end of the game ends. If it's still in the middle of the arena, it's still going, right? So this is kind of one of the reasons that Unreal Engine is nice, is that you can kind of make environments where most of the rules are codified, but then you can leave some of them up to blueprints, for example. And there's, right, you can mix and match between them, or even kind of, you know, call C++ code from the blueprint code. Yeah. So the next topic is kind of the policy, right? So this is what happens. We've done training. We had our environment, we used it. Now you want to actually deploy the model. And this is, you know, we're deploying in Unreal Engine, right? You get this nice exported Onyx, right? So this one has a raycast sensor with 36 rays, yada, yada, yada. More kind of technical information about like which channel it's firing the rays on, because they don't necessarily have to be for visible info. This one detects the position of several other agents, right? And then this one just passes in the state in case you're using like an RNN or an LSTM or other kind of state-based model that, you know, has a history with it. And then you can kind of see just the UI down at the bottom, where you just drag and drop kind of your model inside the Unreal Editor. Right. The last thing is the environment. So this is, you know, represents the other part of the environment and generating the next state, let's say. In general, kind of the meat functions that are specific to Schola are just a simple event. Another way of representing a function that just has no return values, right, is just to do some setup. So you can initialize the age, initialize the ball. Let's say for a game of Pong, right, you have the two paddles and the ball bounces between them. Or resetting it to do some setup there. So all pretty simple stuff. It's mainly just kind of, right, the meat of it is that it takes all this and remaps it, and so it shows up in Python in the right format, so you can then just plug it into Gym. So anything you build quickly here, you can then just deploy, right? And you can build it and have to compile a game, or you can just connect to this running editor, so you can kind of go back and forth and iterate. So a few kind of short examples that we've developed with Schola, just to kind of highlight how to use it. We have, starting kind of in the top, my right, your left, would be an agent that just solves a maze using raycasted movement input. And obviously this is a deterministic maze, so it memorizes the maze. We have an agent that is trying to keep a ball on its head using some rotation, right? So it has to basically try and balance it. We have an agent that can rotate and shoot, and it just has raycast to detect some rolling targets. A 3v1 game of tag in the bottom there. A very simple debug environment where the agent just tries to learn to go to the big reward or the small reward, but preferably the big one. And then at the bottom over here, we have an agent that is following a track, right? So it's basically a race car, and it's going to kind of come around the bend here, although it is quite small on the TV. And it's basically trying to progress around the track as fast as possible and stay as close to the center of the track. So those are kind of 6 examples we've released just to help people kind of see how to use the toolkit, or kind of some example implementations of toy problems. We'll do a little bit of a deeper dive into how we implemented tag and just kind of talk about that, right? So here you can see a snapshot of the environment, and you have these agents, right? And what I've done is I've visualized the observations here. So they have basically the runners here the taggers here can see their teammates, right? So you can see the arrow to the green arrows to their teammates, and the red arrow telling them where the runner is, so they kind of know where to go. And this next one, I believe, no. Oh, okay, perfect. If that will play. There you go. And you can also see that the blue one, which is the runner that's trying to escape, has raycasts that are detecting basically walls and the other taggers, right? So it's trying to avoid them, and they're chasing it down. So I'm going to show up a couple of fun trajectories we've collected from like a well-trained model here. So we have a couple of fun strategic ones. So I'm going to point out this one over here first, right? The blue line is the agent that's trying to escape, and the other 3 lines are the taggers that are trying to tag it, right? So in this one, it starts being chased from behind, it rounds the bend here, it sees this agent coming this way, so it takes like a loop-de-loop to escape, and then it gets pincer movement by these two, right? So there's some fun kind of strategic thinking happening there. And a similar story for this one up here, right? It's being chased by two agents, it kind of loops up around the top of the map, and then it gets jump scared by this tagger that pops around this corner, and it can't see this tagger here because it only has ray cast, right? So it's sending rays out this way, and it can't see around this corner. This agent here, you can see, is kind of mirroring it because it knows where the runner is, right? So it's basically tracking the runner's position. So if it tries to go up, it can go up. If it tries to go down, it can pop out like what happened here. And then it has to double back, and when it doubles back, it's too late and it gets caught. Okay. And so then I'll hand it back to my colleague Mehdi to talk about sim2real.
Thank you. I guess before I continue, so let's have let's have a kind of what we've learned so far, right? I guess it's important to understand what we've learned and what are we doing here. So the first part, we just try to conceptualize what reinforcement learning is, right? But as a researcher, as a student, I guess actually you have a mission, right? So either you are a reinforcement learning practitioner or you are a game developer. Obviously, it's good to know both, right? But it's going to take time, right? So let's say actually you are a game developer. You care about reinforcement learning, but not much, right? In that case, you benefit from Schola a lot, right? Because we basically put everything in a box. Reinforcement learning is using the third-party tools, famous one, well-known one, highly reputable one, right? SP3 or RLD that Alex actually explained. So they are the thing that actually big companies are using them. Many researchers, many academic people, right? And when there is a paper, they try to implement that paper in that library. So we don't want to just keep updating the third-party tools, right? So that's basically somebody's else's job. And then you are a game developer, so you basically design your games, whatever it is. So for example, you think you can come with a very cool idea for a game, right? You basically create that in Unreal. People are going to be excited about it because it's kind of high fidelity and it's Unreal, right? And then now you want to connect these, and then Schola is going to play a key role here. So it's going to connect those third-party reinforcement learning to Unreal. So Alex and the team actually implemented a bridge, right, that connects Python to C# or C++ that is, Unreal is using, right? And they basically read and write from this bridge to see actually Python is going to use this observation Unreal generates and then feed it to the reinforcement learning algorithm. And you don't need to be worried about all those things. And it's going to help you to basically accelerate the focus that you have in game development, right? And at the end, if you are now getting knowledge and experience, right, and you want to play with reinforcement learning as well, then you can play with the reward. Then you can play with the actions. And even if you want to do it more, you can try to implement one of these reinforcement learning algorithms yourself. And then Alex talked about a very kind of open interface, right? You implement that in a way that actually Gym supports, and then it's going to be connected to Unreal. So basically, the spectrum is very, very, very broad, right? So you can start from very technical, highly competitive reinforcement learning algorithm and publish to basically be a practitioner and develop a game that people are going to enjoy. And depends on where you want to do, or if you want to do your research or your bachelor thesis or everything, right? So you have a wide spectrum to pick basically your battle. Now, I guess everything that we talked about was game, right? The question is it just the only thing that actually you can do with Schola? And I want to motivate actually a new aspects of benefiting from Schola. And with that, I'm going to start with the concept of sim2real. Sim2real, as you can see here, is very easy to understand. So if you are working with, let's say, expensive robots, right? You don't want to teach the expensive robot everything from random location, right? So for example, if you want to teach your robot to navigate, the robot is going to hit the wall a lot at the beginning, and it's going to just ruin the robot, right? So you don't want to do that. Instead, we are going to mimic basically the actual robot in a simulation environment, and then teach that simulated thing to do navigation. And then we try to map whatever actually we did in simulation to real. And they call it sim to real. There is a very good literature and history here, right? So people actually tried many different aspects of this sim to real. For a few years, basically, people published in Nature, right? So, for example, they teach drones in competitive drones race, right? So you can find those papers. Or we saw basically racing cars, right? From some companies, and they try to basically teach this race car to be a champion, right? And you cannot beat it, right? And then it's going to win everything. But how did they do that? They basically started with sim, and then they kind of map it to real if necessary. Now, this is the concept of sim to real, and we want to see actually how to do it. So we were fortunate enough to have some collaboration with universities, and also we had a very good intern, a student who wanted to do something extra, and he started to look into this. And to be able to do this, we said, okay, let's not basically go pick a very kind of luxury robot, right? Instead, because luxury robot come with a lot of sensors and everything, and it can be easier or it can be harder, depends on your objective, right? However, we basically picked a toy, let's say, car from Amazon, and we wanted to see actually if we can teach this toy car using a Schola to be able to kind of derive a smart, right? First, we started with a simulation version of it. As you see, there is no similarities between the appearance of this. It's not important, right? What's important is the capabilities that we have in this car, right? The capabilities are, can this car, I don't know, go left, right? If this car goes left, right with one speed, this car needs to mimic that, right? The appearance is not important. What type of observation this car has. So for example, if you have a camera here, or if you have radar here, this car needs to be equipped with that, right? Because we want to mimic the reality in the best way that we can. And then this car is going to learn how to drive, and then we just convert that to real. So first step for us is to understand actually what this car is going to do, right? So we said, let's read the spec, what's the max speed, what's the turning radius, what's the weight, what type of sensors we have, what type of controller it has, and at the end, what type of programming language we use, right? So as you can see, it's using this Raspberry Pi, right? And there is a maximum TOPS that actually this Raspberry Pi is capable, right? So the model that we are going to train needs to be aware of that, because if you have a really complex model, you cannot just convert it to something that a Raspberry Pi 5 can handle, right? So these things are the things that actually are important: the type of observation, the amount of compute, the type of action, and then the physical characteristics of the robot or car or anything you want, right? For example, why this weight is important? Because at the end, the car needs to the actuators, the Onyx file that you're going to extract, these things need to be able to move the car, right? So you need to be aware of the mass, right? The weight. Now that we know this, so we basically created this car in Unreal. We put all these things inside this car. You cannot see that, but the weight is going to capture whatever actually we talked about, the sensors, the actions, everything. And then we trained it with a Schola. And this is kind of the training. It shows the reward that it gets and everything. So at first we said, let's do the minimum, and the minimum that actually we wanted to do is just follow this white line. So obviously, maybe when you were in high school or even middle school, basically you tried this kind of robotic story, right? But in those days, you didn't try reinforcement learning. You just basically said, let's write a microcontroller program and then use the sensor to follow this link. So right now, actually, we are not doing those. It's based on reinforcement learning. So we basically put an AI model, a few layers of multi-layer perceptrons in this car, and then we are going to get the observations where the car is, I don't know, where the line is and everything. And based on that, we train the car. And as you see, the learning case shows that basically after some time, the amount of reward that the car gets is going to go up, which basically shows the car is learning, it's converging to something that is good, right? Now that we see this, we are going to do it in practice and show that actually now how it's going to work, right? So we basically exported the model, and then we put the model inside this real car, and there is no rust, nothing, right? It just basically we exported the model, we programmed the microcontroller using the approach that actually the car developer told us, and now you can see actually the real car started to follow the line, right? And everything is based on reinforcement learning. Maybe, to be honest with you, is a 2 weeks work, right? For somebody who already knows Schola. So if you want to do something else, obviously after defining the project, you can target some of these things as your project. What's the benefit of this sim to real? Maybe as a kind of high level, it's good to talk about those, right? First of all, it's going to reduce the cost and time of training. Reduce cost because you can just virtually create it. You can randomize it. Whenever actually the car hits a wall, you don't need to just grab the car, put it somewhere. It's going to reset automatically, right? You can randomize the initial location of the robot, everything. Everything is going to be fast. You are not going to pay any cost. The robot is going to stay safe, right? And then at the end, you can easily escape the training, right? So right now, actually, we just had a very simple environment. But if you have a very complex environment, then in that case, you want to scale the training, run on multi-processors, multiple clusters, right? And then you can do all those things and train and then use it. And at the end, sometimes when you transfer that to the real case, you see actually the benefit is not clear. Then you see what's going on in the simulation. You try to create a corner case that actually was kind of lacking in reality in the simulation, and you're going to close this loop back and forth, right? Now we saw actually line following, and then we wanted to extend that, and we said let's now use the camera that we have in this car to find basically one object, right? It's a little bit more complex. So for example, assume that you have a car and then you put your hand in front of the car stops, and then you move your hand, the car is going to run, right? We wanted to basically go from here a little bit further, and we said let's basically understand the color as well, right? So for example, if you move your hand, but your hand is yellow, the car is not going to come to your hand. The car is going to just detour, right? And if it's red, it's going to come to your hand, right? So this is basically a little bit further, and first we basically did in simulation. In simulation, everything is good because you have beautiful background, you have very specific colors, everything is good, right? And then we wanted to move it to a reality, and you're going to see that the car learns actually to go to the red one, right? Now let me add a few things. So when, as you can imagine, right, when you move to real case, there are some obstacles. In our case, even if the problem was small, we realized that basically the background color and not matching the real red and let's say white with whatever actually we had in Unreal is going to confuse the robot, right? So in that case, you have two options, right? One option is to fix your environment to match it with reality, which basically was the case for us because nobody was paying us to really teach this robot to just do a good job in reality, right? So for us, it makes sense to mimic basically what we had in reality, in simulation, in reality. However, sometimes you are basically developing something real, right? For example, you are developing a robot to just move around in, let's say, campus, right? In that case, you cannot change the campus. Because of that, you need to see actually what's wrong with the robot and try to put that back in the simulation. So, for example, if your robot is not good with, I don't know, dark shirts, right? Then you need to try to put a crowd in your simulation that wearing dark shirts. And then the robot is going to learn, okay, dark shirt doesn't mean just black. It means brown, it means different colors, right? So you need to be smart, you need to observe what's going on, you need to feed back the data. In our case, we just basically talked about it, and then I asked my intern to go to one of these dollar stores and basically buy some kind of black color and some kind of cardboard, right, to create a very beautiful ideal environment for these. And then now you see actually we use the same laptop that we train, and everything is good, right? Because the robot actually already knows the laptop's color. If we put some kind of red ribbon, it's going to be different, right? Because that red is not this red. However, for our case, we wanted to have a POC, have a prototype, right? And just as a researcher, sometimes you need to pick your battle, and we picked to not basically train this toy car to be the perfect red follower car, right? Yeah, with that, I guess actually we covered a lot of different things, and I'm going to close the talk with a few takeaways. The first thing is AMD actually is really into open sourcing, right, and providing the opportunity for people to be able to build something on top of it. We released AMD Schola using MIT license, which basically means you can do whatever you like in a way that actually defined in the license. So first, that's the first takeaway. AMD Schola is open source. You can use it for reinforcement learning into Unreal Engine. The second one is basically this is the Git report that we open source it. You can just scan this QR code to get to it as well. So basically this goes the location that we have. Alex talked about some examples. The team is really into having multiple releases per year. So this year, I think actually we had 3 already, and we plan for a few more, maybe 2 more, with different features and some examples and some blogs. And if you are willing to contribute, we welcome you very much. In case actually if you want to develop some examples, or if you want to develop something a little bit more challenging like the one that you see, so you are welcome to contribute. Obviously, it's MIT license and open source. You can release yourself, or you can create a PR, and the team is going to basically review, provide feedback, and at the end you are going to manage it. So you can do reinforcement learning for NPCs. You can do reinforcement learning for sim to real. And we look forward to seeing how community will use AMD Schola to develop, let's say, more advanced NPCs or more stuff related to sim to real. With that, I close the talk, and I would like to open the floor for Q&A. Thank you.
Thank you so much. That was really fascinating. Both of you. We have lots of time for questions, so thank you, Sean.
Yeah, thank you. It's a really nice talk. In AMD Schola, is there a specific reinforcement learning algorithm you're using, like Q-learning, for example, or does it provide a variety that you can choose from?
Yeah, so part of our kind of design philosophy was to not restrict that, right? So, right, OpenAI Gym doesn't like prescribe any kind of algorithm, right? It just describes like what happens in the environment when you say, I give the environment this action, and then it comes back with observations or words, you know, whether the environment is complete, you know, any other kind of odds and sods and like a, you know, extra data, right? So we're basically agnostic to the algorithm, right? And we provide direct support for like SB3 and RLib, right? We have kind of like direct environments for those frameworks, but you can still go to them. You basically could do Gym to SB3, right? So like Schola, Gym, SP3, you can do Schola, Gym, RLib, but you can also just go straight from Schola to SP3 and RLib, right? And then those frameworks provide a wide variety. I believe SP3 has Q-learning in it. I know it has PPO, A2C, et cetera, et cetera. And between the two of them, you have pretty much all your bases covered in terms of different approaches, right? But also, because we go to Gym, if you find like an open package that has Q-learning, it probably supports Gym because that's kind of the de facto standard at this point.
So Scala just provides the information needed to use any approach.
Yeah, pretty much. We try not to be on the algorithm side of things.
Okay.
I'll leave that up to developer or researcher or whoever else is kind of working with it.
Nice.
Yes, again, thank you for the great presentation. If I got it right, Schola is more of a intermediary between other projects, right? You have the Unreal Engine that provides the physics and the environment, and you have the libraries like RLib and Gymnasium that provides the reinforcement learning functionality, and Schola makes it easier for you to glue them together, right?
Yeah, I would say so. I guess they're not like those two projects are not our projects per se, right?
Yes.
It is, and I'd say right now there's some other frameworks that do similar-ish things, slightly different approaches, let's say. Right, we're the only one that I'm aware of that maps to Gymnasium at this point. But so basically, without kind of Schola or one of the other frameworks, you wouldn't have any glue, and you'd basically have to do all of the mapping yourself, right? You basically have to like write a communication channel that sends data between the two, et cetera, right?
Yes, yes.
Yeah.
So I'm looking at the documentation for Schola, and I feel that the bar for starting with working with it is relatively high because you have to manually install Unreal Engine. You have to then install Schola as a plugin inside a Unreal Engine project. Are there any plans to come up with a more automated distribution style installation that would pull these different projects together and you don't have to do everything manually?
Yeah, that is one thing we're looking at. Ultimately, you'll still have to install Unreal Engine, right? That's mainly because that's not our product, right? So we can't distribute Unreal Engine to you, like that's never happening. But we can basically improve everything else, and that is on our kind of to-do list to say, like, once you have Unreal Engine, how can we make it easier to get Schola in your hands or get it working with what you're want to build, right?
You could buy the company.
Yeah, I'm not sure what's the installation process for Unreal Engine is, but if it is scriptable, I suppose there would be a possibility of you download the Unreal Engine install yourself, put it into a folder, and then you run a script that would do the process for you. Would that be
well,
possible?
Let me actually rephrase what you are asking and say, assuming that you have Unreal, how long is going to take to have a Schola, right? In terms of the process, right? Is it 15 minutes? Is it 2 hours? Is it 2 days?
Oh, like if you want to put Schola in it, right now it would be, I'd say 15. The goal is to get that down to like 2, because Unreal Engine supports like a marketplace for plugins, right? So basically you just go to the website, you click add, and then it would show up in your Unreal Engine editor, your project, right? So that is basically the thing I'm referring to when we say we want to basically push our support that way, right? So you have Unreal Engine, and when you go to launch Unreal Engine, it'll give you like, it'll say like your versions of Unreal Engine, and then underneath it says plugins, right? And so basically under there, it would show your list of plugins you've added from the web marketplace, or even a link to go to the web marketplace to add them.
I guess
Right,
actually,
so-
remember, I don't know, 2 days ago or something that you were trying to install a new package, right? You need to pre-install it. It's going to be the same, right? Sometimes conflict of package versioning and everything. So it's kind of, in machine learning, everybody is aware of that, right? So, so whatever actually Alex is saying, so we have some kind of requirements, right? So for example, PyTorch and RLib, SP3, this version, that version, right? So you need to, we already have a requirement.txt that basically just map all these versions. At the same time, you need to, when you have Unreal, right, you are going to basically enable that, and it's going to take, let's say, 5-10 minutes, right? So that part I'm not worried, right? I guess actually now that you have the plugin in Unreal, The question is how much time you need to come to your first example. Now I'm going to answer it in a way. So if you have experience with Unreal, so if you are comfortable with creating a cube and then a ball in a room that's chasing each other, then the next, so it's going to be, I don't know, if Alex wants to do it, it's going to take maybe 30 minutes, right? Maybe 15 minutes. And then after that, you are going to enable a Schola for this particular thing. And it's going to be fast because you need to define the reward. We already have the blueprints to define the reward. You just need to basically drag and drop things together to glue it together, as I said.
Okay, but so familiarity with Unreal Engine is always going to be a requirement for using Schola.
Yes, yeah, because it's based on Unreal, right? And familiarity with Unreal can be after watching 5 hours of YouTube videos, or it can come from many years of experience playing with Unreal, right? Obviously, you can be good after 1 day, or you can be good after 5 years.
I'm just trying to think about the relation between the projects. So is the idea that Schola is a component within the Unreal ecosystem? Oh, okay. All right, thank you.
So, are you using acceleration only on AMD GPUs, or are you supporting the?
No, it's PyTorch based, and if you can just use PyTorch with whoever, then it's going to be fine.
So thank you for your presentation. I have basically 2 questions. One about the Unreal Engine and the second one about the Schola. So we used to have the gym to build the environment for research purposes, and I saw the Unreal Engine as well. So if I'm not mistaken, it's used mostly for the environment that they are using the 3D objects. So if you use the Unreal Engine to build an environment, do you still need to use the gym for completing the environment or not? That's my first question. The second question is about the policy network. So I saw that your Schola is using the stable baseline. So in the SV, we have a limited networks for the policy networks, like the feed-forward neural network and so on. Is it possible within the Schola to define our own custom network, like the GNN and so on?
Yeah. So I'm going to answer the second question, and then
take the first one,
you take the first one. So for the second question, so right now actually we support SP3 and RLlib officially, which basically means we have examples for the analyst, right? So in-house, we basically try Torch RL as well. So I'm not sure actually if you are familiar with it, but in Torch RL you can just do everything, right? But it's going to take a lot of effort, right? So the short answer is if SP3 actually has this contribute repo as well, right? So some of these not standard algorithms are in that repo, right? So you can basically benefit from those as well. So there is nothing against it. At the same time, for example, if there is a multi-agent algorithm in RLlib that you want to use, you can also use that. If you want to just, for example, implement a transformer, right, or a CV model, right, or for example, use one of these or Hugging Face models, right, then you need to basically, it's not a Schola anymore. It's before coming to a Schola, you need to be able to, for example, train the cartpool example in you know that, right? So you need to be able to train that guy with, let's say, CNN or GNN or other things, right? When you are successful, then the rest is your environment is a gym environment, a Schola supports that, right?
Thank you.
Maybe I'll add a little bit to that. I think a short blurb about the, kind of like the high level philosophy might like explain or answer that question, like help answer that a bit as well, right? Kind of we see our users as being like bimodal in a sense, right? We have kind of game developers who care a lot more about building the game, and then they just want to like train a model. They don't really care about, right, the algorithm used. They're not interested in bringing their own algorithm, right? Unless they're doing it to solve a specific problem. They more so just want to have RL in their game, for example, right? So that's kind of one use case, right? So they want like we see them as wanting like a fast kind of hit play and it runs, right? So for that, we kind of have this built-in quick support for SP3 and RLlib, right? Where it's direct, and basically we support a limited set of the options, but they're kind of accessible from, let's say you open your Unreal editor and you hit play or simulate my level, and then it starts training, for example, right? So that's kind of a different use case than, let's say, a researcher, right? Like the researcher wants to open it, play around with the algorithm, tweak the environment, try different things, right? And so then for that, we have kind of much more open-ended support through GIM, and also kind of, you can bring your own SP3 model, anything else, right? So that's kind of, we support those two things in slightly different ways, right? We have like a quick way to do it where you press play in the editor, and maybe your options are a bit more limited, or if you run it from, let's say, like you basically can drive the process from Python, right? You can do whatever the heck you want, because it's just another GIM environment, right? So I think that's kind of our high-level design philosophy, right? So if you see us saying like there's a fast path for SP3 and RLib, it doesn't mean that that's how you have to use it. That's just something we have in place so that when we have a game developer come and say, I wanna just get something going, get a prototype working, that's for them, so they don't have to learn how to do RL and everything else like tune hyperparameters first. Yeah. So then, for the first question, do you mind just reiterating again?
Yeah, sure. So I want to know, is the Unreal Engine is good enough to build an environment, or we need to have the GIM as well to build an environment?
So the way it's set up, basically what it does is that you set up like something in Unreal, right? I put got like a little character in the scene. I put, for example, I'll go back to one of the examples over there, right? Let's do the tag one, for example, right? So I put my agents in my scene. I add a raycast sensor. I add another object in Unreal that handles kind of tracking the positions of the other characters in the scene. I put my walls, my everything else, right? And then what Schola does is it's going to, when you connect that to your Python, it's basically going to come up with a GIM like environment that says these are the agents in the scene, these are their observations, right? And then it's going to basically pipe the actual observations they collect to the GIM like step function, right? So then you don't really, you need GIM because that's kind of the bridge or the API that we're supporting, but you don't need to do anything else in Python beyond, say, connect to my Unreal editor, and then it fills in the rest from there. And that's kind of the kind of core of what we want to like support, right? That's kind of our core value that we think we bring.
So if I understand, even if you use the Unreal Engine, we still need to use the GIM to implement the step function, define the observation space.
No, that's provided for you, right? You implement it in like essentially you provide that information on Unreal, right? So if I put my agent in the scene, I put a raycast on the agent. When I call step in Python, right, on my GIM, that's going to be filled in from the raycast in Unreal, right? And it's going to handle just like translating the Unreal stuff to the Python stuff, right? So then you don't need to do anything else in Python, right, to like remap anything like that. It'll handle kind of, naming your observation, putting the right spot, and then, when you call like step in Python, it forwards it to Unreal, collects the raycast, sends it, brings it right back, right? So,
Sure. Thank you.
You go ahead. We're too polite here, we can.
So I attended late, so you may have already answered my questions, but I'm going to ask it. One is about if you have on your pathway to expand this to Unity, for example. And this one, and also second question is if it makes any sense, or you also thinking of using this under VR model where you can also have it wear the glass and also observe and so forth. I hope my questions.
No,
make
it's
sense.
clear. Yeah. So for Unity, I think it's so we basically consider this, right? But it's not going to be immediate. And then for VR. I think actually, so we have a roadmap, right? Internal roadmap. So there are features that actually we want to add. So these things are basically are in our roadmap, but not very top in the list, right? Depends on our connections and whoever actually is going to use it, right? So these basically are going to be shuffled. But yeah, they are good things to be considered for sure.
So Unity is in.
So Unity already has this ML agent. You already are aware of that, right? So the question is actually if we add any value to it, right? So that's basically something that first we need to figure out. And then Unity's market is different from Unreal market, right? So we need to see actually which market we need to approach, right? So there are big questions that we need to answer before coming to a conclusion.
So thanks, great presentation. So probably related to Ellie's question is about how this scales to more realistic, complex environments. There's a lot of back and forth between the learning library and Unreal Engine, every iteration of learning, right? So in more complex scenarios, the observation space can be really big, and we can collapse that down in Unreal Engine, or we can pass that off to the learning environment, right? And I'm just wondering if you have any comment on the weight of the interface, the message passing and so forth, and how that would determine how you'd approach that.
So reinforcement learning usually is not sample efficient, right? Which basically means you need a lot of interactions. When the model is complex or the observation space is complex, it's going to take even more, right? So usually people actually handle observation in not very kind of flat way. So for example, they have this big observation space, but they don't feed it in directly to the model for Unreal. They basically add a CNN model first, right, to segment anything, right, for example, or to basically extract the depths, right, and then the latent space is going to be fit into the so that's basically one approach to do it, right, and then it's going to reduce the complexity of the problem a lot. So the other thing that you can do to handle large number of actions is to basically have these small models responsible for a subset of these actions, right? And then it's going to basically break down the whole training into some specific policies responsible for some good things, right? For example, let's assume that you have a big brain, and then part of your brain is responsible for handling conversation, the other part is for, and then you need to glue them together, right? So you can use a behavior tree to glue this together. So if an enemy is approaching, so that part of the brain is going to interact, right? We already have this BT plus RL in Schola, so we released that I think maybe a month ago or something. So we are going to add to this, but the concept is you have a big behavioral tree, and then the leaves are going to be the models, right? A small model is responsible for doing things that matter. For things that are so easy, we just use rules, and then we connect everything together to construct a very complex behavior.
I guess a more philosophical question related to Ellie's question is, does this mean long term that we'll see more integration of the RL libraries into the engine, or whether your approach is this just a stopgap measure, or?
So that's basically a very good question. So community already started to look into when RL is going to be used in games, right? And they basically highlighted a few things that can be done, right? So there is basically a long-term goal, and there is kind of some, let's say, short-term approaches that you can take to use it, right? So the approaches that I explained are going to be short-term, right? So in short-term, you can have a very complex bus NPC with many actions and many observations, but in the long term, if you want to give the whole control to RL or to AI, then it's going to be, so you need to have a lot of compute, right? You need to train it for many weeks, right? To be able to do that, yeah.
One more. Kind of on that note, is there a way that the plugin could be used in real time to like dynamically learn in the game setting?
Right now, you could set that up, right? Mainly, we're looking at kind of inference performance, like for games where it has to be pretty fast to like not bottleneck the game. So we've mainly looked at like use cases where you train the model and then you basically, Onyx like deploy it to kind of your inference engine so you can run it as fast as possible, right? And obviously, if we're training the model in real time, that precludes the use of Onyx and kind of a standard inference engine because we're not inferencing anymore, we're training, right? So that being said, you could still like basically just connect to Python, right, and run a gym environment while the game is ongoing, and do whatever you want from there, right? The sky's the limit, right? Because it's just it's just a gym environment, so you could put on any kind of like continuous learning algorithm, anything else, right? Your policy is now in your arbitrary framework of choice in Python. But this isn't necessarily something we are like testing or like really kind of exploring at this point. I think it's something that we've heard a lot of people are very interested in, or like have been are you guys going to do this? So it's something we are definitely considering. But right now, as Maya said, there is a lot of open questions and areas and extension points. So it's not one that I think we're going to like be tackling in an official manner in the near future.
So there is another there is another dimension to it, right? So you can just play with the game, right? But it's not going to change the behavior of the agents very soon, right? To be able to agent to observe actually what you don't like, you need a lot of interaction, right? And at the same time, I want to highlight. So for example, the self-driving car, right? So right now, actually, there are a lot of cars that are kind of collecting observations and actions and then send it to things, right? But as you can imagine, many of them are very common. The agent already saw those, right? So to be able to teach the agent in real time something beautiful and new, you need to really see actually what type of observation and action that you are collecting is new, right? You cannot just, for example, drive in a city in a very beautiful sunny day, right, and say, okay, so I'm collecting new observation for my agent, because the agent already saw those, right? You are using that in self-driving car. You need something that is not, so for example, you need a construction area with snow, right, and with basically nothing is visible. You need some very specific things to be able to have some useful impact on your agent. Now back to your question for game, if you want to play with your character and make your character smarter, you need to be patient, right? You need to play this interaction for many iterations, and you need to just make sure that every time that you play, there is a repeatedness there, right? So you cannot just basically assume that your agent is going to just pick the thing that actually you like, right?
Do you think you could try to almost, I mean, I know it's hypothetical, maybe just fun thinking, but do you almost think you could extrapolate from like a few examples that the player does to
there is this
build that up?
There is this concept of synthetic data generation, right?
Yeah.
You can use the statistics or machine learning or diffusion models to create basically a data set from another data set that you have, right? So you can go that, it's a research problem, and there are already some very beautiful things that you can benefit from.
Right.
Another question. You mentioned the sim-to-real gap. A lot of that gap is not conditioned on actions, right? It's deployments and so forth.
Yeah.
So can you comment on what's going on in research to automatically close that gap, so to build or fine-tune the simulation environment to match the statistics of the real data?
Because it's kind of very specific to the problem, as you can imagine. So, for example, if we are trying to train an agent that basically gain maximum coverage of an area, right? And then the dependency there is going to be different from if you are going to train an agent that just show good emotion, right, or something, right? Because it's very specific to the problem. So researchers usually define, okay, this problem is very important, now we're going to tackle that, right? For example, for the paper that I talked about, for the Nature paper that they trained these drones for championship level, in that case, basically the drone itself needs to be very fast, right? Really fast. And then when you are fast, your cameras are not going to capture everything perfectly, right? Then noise in camera was something there, right?
Mm-hmm.
And they wanted to see actually how they can add Gaussian, for example, noise during simulation to camera to capture that. And to be able to find basically the parameters for this Gaussian noise, they need to collect a lot of data during this real thing.
Mm-hmm.
And then scientists sit there, analyze all this data to find the parameters for the Gaussian noise, and then they provide that inside the Unreal, right? So it's a kind of very beautiful research problem that you need to tackle, right? But the answer is problem specific. Sometimes actually the problem is in the camera, sometimes the problem in the engine, sometimes the problem in the actuators. For example, sometimes actuators are discrete, right? So you need a continuous actuator. In our car, very toy example, right? But if the radius is not good enough for you to detour, then it's not good enough for you to tutor, and you cannot do anything about it, right?
You gave examples of just colors being different, so forth,
Yeah.
and you could approach that with an adversarial approach potentially, and just looked at images even. And
Yeah.
to
Yeah. In particular, we didn't want to really make it better, to be fair, because, as I said, so it was a POC for us to focus on the Schola part, right? We wanted to just get from Onyx to real, and that was the most. Sorry.
Yeah, so I have a question. There's a project in NVIDIA, it's called NVIDIA ASXM, so which does a really similar function as yours. And I was just curious, what's the difference between your project and this NVIDIA ASXM? And well, can you elaborate more on the robotic simulation part?
Yeah. So we are basically benefiting from Unreal, right? And what does it mean is so whatever actually you can do in Unreal. So we are not focused on the simulation part. And that was a decision that we made to basically focus on something that the community loves already, right? And then for acceleration, we are using PyTorch, right? If PyTorch is kind of good with one particular accelerator, then it's going to be fine for us. So for us, we are connecting Unreal to games and to ML practitioners, right? And then for the second part of the question that you have is about robotics, right? So I'm not sure actually if you were in the talk, but we basically try to move from games to robotics, right? And hopefully we are going to expand on that in future, considering the collaboration that we are going to have.
Maybe I'll add a sense or two on that. I think a more apt comparison would be like Isaac Gym, right? Which basically takes Isaac Sim and then connects it to Gymnasium, right? So like kind of the analog for Isaac Sim would be Unreal, right? So that's kind of, basically we're not pushing Unreal, it's simulation quality, right? We're leaving that to the Unreal developers. So I just wanted to add that bit of context that maybe like the comparison's best between Isaac Gym and us.
Any more questions for maybe Alex? Okay, well, that was really amazing and really interesting. Thank you. Thank you all for coming. That's great. Thank you. Good turnout, actually. This is this time of year.